So this is about maximum power point tracking of a photovoltaic cell. So in this we need to track the maximum power from the cell to improve the efficiency of the cell. So if we observe here and all, so that is based on the operating voltage and current. So here and all the power is minimum and here the power is maximum, and from here also the power is minimum. Why? Because here the current is constant and voltage is increasing, so power is also very linearly varying like this. And here voltage is increasing but current is decreasing, so power is decreasing like this. So here only we'll get the maximum power, so it should be shown here. Sorry. Mm, this is the maximum power, and here power is decreasing in this manner. Okay, so and here this is a open circuit voltage and short circuit current. That is by by open circuiting this load terminals. If you remove this load, the voltage available at this end is open circuit voltage, and by short circuiting this terminals with a wire, we will get a short circuit current ISC. Okay, then here. So that is this thing, two things. So fill factor, it is VMP IMP by VOC ISC. So this is the voltage. So this is the current and this is the voltage corresponding to maximum power. And this is so this outer rectangle represents VOC ISC, and this inner one represents VMP IMP. So area of the inner rectangle to the area of the outer rectangle will give us the fill factor. So fill factor should be maximum. So under lower radiation conditions, the PV characteristics will be decreased like this. So the fill factor will also be getting down. So here is the electrical tracking. By changing the voltage or changing the current, we can change the operating point to a maximum power point. So likewise here we have a mechanical tracking. In this we are mechanically changing the panel only. Okay, so before case the panel is fixed and we are changing the voltage. Here instead of changing the voltage or current, we are changing the mechanical angle of the panel towards the incoming flux, solar flux, this incoming radiation from the sun. So it follows our sunflower, as the sunflower also tracks the sun continuously from day to evening. So this panel will also follow the same technique. So here we have two kinds of trackings, one dimensional or two dimensional tracking. So sunflower usually for a two dimensional tracking system. So in this we have one dimensional, two dimensional tracking systems. So here this azimuth will track. So here is there two kind of two dimensional tracking. In some cases in real time only this tilt only adjusted. In some other cases this azimuth and tilt both are controlled in order to track the power efficiently or effectively. So this is a block diagram of a PV system, and this is a PV panel, and this is a boost converter, DC to DC converter, maximum power point tracker and charge controller circuit, and this gives the control signals to this buck or boost converter, and this switch. When this switch is open, all the current try to charge this battery. When the switch is closed, it will fed the current to the load. So the load current will be available from this as well as from this battery. So this is the mppt, that is the circuit actually in this one. This is a detailed structure. There's a PV panel and this is a PV voltage C1. By controlling the duty cycle of this one, we can control the voltage at this end. So by controlling the voltage, we can control maximum power point also. So duty cycle can be controlled by detecting a signal voltage and current from this using sensor, and there is a program running inside that is a perturbation and observation algorithm, or it may be an incremental control. So we have so many methods to track the maximum power point. So there the power will be calculated So whether the power gradient will it be increasing or decreasing based on that. So here if you observe the dp by dv change in power with respect to change in voltage is positive here, but here it is negative. So where the transition occurs from positive to negative, and that region is considered as maximum power point. So that will be done inside the so inside this microcontroller, and accordingly it will generate some duty cycle of this one. When duty cycle increases, the voltage is increased. When duty cycle decreases, the voltage will be decreased. Duty cycle means delta that is equal to v naught by v in, that is on time, t on by t, that is the duty cycle. On time increases, the voltage increases. When on time decreases, voltage decreases. This one is decreased. So when this is turned off, this capacitor gets charged to a certain extent. There is a strong capacitor, and when we turn on, when turn off it is charged, when turn on, and then capacitor is discharged to this one and charges the battery in this manner. So the voltage is getting down a bit. Again, if it is not tracking the maximum power, again we have to change the duty cycle and further charge the capacitor until it tracks the maximum power point. So that's what we actually set by this circuit, and here through this inductor it is charged. So it is a buck converter model, and there is another converter called boost converter. In buck converter, the output voltage is less than the input voltage. In boost converter, the output voltage is greater than the input voltage. Okay. So in general, we prefer the boost converters. And here the change in the characteristics due to change in temperature and irradiation. So this lambda is solar irradiation, which is calculated in watts per meter square. And so here Ig, that is our IPV, photocurrent. This Ig represents the photocurrent. Photocurrent equal to ISC plus K into TC minus 25 into lambda by 100, where lambda is irradiation. You can represent this with S or lambda. And so based on the changing in the irradiation, this current will also be changed like this. If increase in irradiation, it will be increased like this. Charge current increases like this. So characteristics will be drifted towards positive for increase in current. And for increase in temperature, it will be drifted towards this like this. So here the temperature dependence. This I sat or I naught is a diode dark current, and then we'll get like this T by T here into this one. This is a saturation current. So this V naught, actually diode expression is I naught into e power QV by KT minus 1. QV by KT, V equal to here V naught into I plus I naught plus RS. If you see here, so this is the voltage in the diode expression QV by KT minus 1. So here is V. V is obtained as V is equal to drop in this resistor plus this voltage, that is I into RS plus V will give us the voltage at this point, that is mentioned here. Sorry, V naught plus IRS dq by dt. So this is this V naught is output voltage of the PV panel. Okay, thank you.